So this is kind of the simplest example of friction. You have some object. It's on a horizontal surface, and it's sliding, has some initial velocity, which I'm not going to specify. I'm going to show you how to do this, but I'm not going to put any numbers in it. This has some mass m. It's moving this direction. So the friction is going to be pushing in the opposite direction. And after a period of time, it's going to slow down, and then it's going to stop. So there'll be, let's call this V0 instead of the initial. So time t equals 0. You have some value V0, and then it slows down and it stops. So the final velocity is 0 meters per second. So using Newton's second law, we're going to draw a free body diagram of this block. So you have the friction force pushing that direction, you have the weight pushing down, and you have the normal force pushing up. So that's friction force, this is weight, this is the normal force. And we're going to define a coordinate system so that moving to the right is positive x and up is positive y. So when we sum the forces in the y direction, because it doesn't move in the y direction, we know the sum of the forces have to be equal to 0. And before we do that, though, let's draw this free body diagram over here with just the forces. So you've got weight going down, normal force going up, they have to be equal to each other, and then you have the friction force. This is the friction force, this is the normal force, this is the weight. And we know the weight is equal to the mass times acceleration due to gravity. Okay, so when we sum the forces in the y direction, this is x, this is y, we have the normal force going up, and we have the weight going down. So if we solve that for the normal force, that's equal to the weight, and the weight is equal to the mass times acceleration due to gravity. Now in the x direction, because we do have movement, it's going to move and then it's going to stop. We have some kind of acceleration causing it to stop. So we have the mass times the acceleration in the x direction. So that's this side. The left-hand side is the sum of the forces, and the only force we have is the friction force, but it's going in the negative x direction. So somehow we have to get the friction force. Well, anytime we have friction, we have to relate the normal force to the friction force, and we do that through the relationship that the friction force is equal to the coefficient, kinetic coefficient of friction times the normal force, not equal to the weight, but equal to the normal force. On a flat surface, the weight is equal to the normal force. So you get mu times the normal force, which is the weight from here, and then the weight we saw earlier was the mass times acceleration due to gravity. So now we can plug that into the sum of forces in the x direction. We get the mass times acceleration in the x direction is equal to negative mu mg. And so to be able to solve how far it slides and how long it slides, we need to know the acceleration. That's what we use Newton's second law for. So we want to solve for the acceleration, which is going to be in the negative x direction. So it'll be negative mu mg divided by m. M's cancel out, and you get negative mu times g. So if we're given the coefficient of friction over here, which we usually are, and we're given the acceleration due to gravity, which we know is 9.8, we're going to get a number. So this will be something you can calculate. And then you can use that acceleration in any of the 4 equations the ones that we typically use are either v is equal to v0 plus at, or we use v squared is equal to v0 squared plus 2a delta x. So if we're given v0, and we know that v is 0, and we know the acceleration, which we've just calculated here, we should be able to calculate delta x from this equation. And we can also then calculate t from this equation. So you solve this one for t. And if we know v, v0, and a, which we would in this case, we can also calculate t. So that's kind of the simplest case. So that's the, we'll call that the moving object slowing down on a horizontal surface due to friction. Okay, so this is a block sliding down an inclined plane. So if the angle is large enough, well, actually it doesn't matter. There's no friction. It's going to slide down, irrespective. So we take our little block, we bring it down here, and we show the forces acting on it. So we have the weight, and we have the normal force. So that's all we have in this case. That's the normal force, that's the weight. So if we clone those and bring them over here and center them as such. Oops, didn't need to do that. Trying to get this thing. Let's try it. Not sure why I can't. Trying to get it so it puts a little cross there, but it doesn't. So anyway, plan B. Oh, there it goes. So we define the coordinate system. I'm going to define x going down because that's the way it's going to slide. Y is going up. So what we do is we convert the weight into a component perpendicular and a component parallel to the surface. The angle of the wedge is this angle here. So we'll have W sub y, and we'll have W sub x, and we'll have the normal force. So for some of the forces in the y direction, going in the positive y direction is the normal force. Going in the negative y direction is the y component of the weight. And so this would tell me that the normal force is equal to the y component of the weight. But since there's no friction, we don't really need this. The only time we need the y equation is if we need to relate the normal force to the friction force through the coefficient of friction. So that's interesting, but it's not useful in solving this problem. If you sum the forces in the x direction, that's equal to the mass times the acceleration in the x direction. And the only force I have in the x direction is W sub x. The way that I've defined x positive going down, I'm going to say W sub x is positive. Now from geometry, we can see that the x component of the weight is equal to the weight times the opposite side from the angle, which is the sine. So it's the sine that we use. And we also know that the weight is equal to the mass times the acceleration due to gravity. So you see that the x component is mass times acceleration due to gravity times sine of theta. So I can plug that in, and so the weight is mg sine theta. Masses cancel out. So the acceleration in the x direction is equal to the acceleration due to gravity times the sine of theta. So if we had a problem like this, we could either start at 0 velocity and calculate the final velocity. So one possibility would be, given that the initial velocity is equal to 0, they would say it starts at rest or something like that. We also know a sub x is equal to g times the sine of theta. So we have the acceleration, and we would figure out the velocity at some other time or distance. So you could specify either, you need to specify either delta x or t. Most of the time you'd expect to specify t. Delta x is positive because you would be sliding down the ramp, which is in the direction of positive x. So we'd have a positive value for delta x. T, of course, always is positive. So you can use, again, you can use v is equal to v0 plus at, or you can use v squared is equal to v0 squared plus 2a delta x. In the case of when it starts from rest, that's 0. Acceleration is going to be positive. Delta x is going to be positive, so you get a positive number here. So, the final velocity is the square root of 2a delta x, and then you could use that velocity to calculate the time. So even if they ask for, if you specify time, then you could use this equation to calculate v, and then you could use this equation to calculate delta x. It's either one. The second case would be that you're given some initial velocity. So you're given v0 equals some number. So you're given that. It's going to be positive. Well, if it's going down, it's positive. So you could have the initial velocity going up. So v0 up ramp would be negative some value. And v0 down the ramp would be equal to some positive quantity. Again, this up the ramp is opposite the direction that it defined positive x. So you'd have v0 negative, and then if you push it down the ramp, get it started going down the ramp, it's going to be negative. Down positive. Okay, so you'll be given some initial velocity. We know that a sub x is g sine theta. So that's positive. So it's going to either, if it's going down the ramp initially, it's just going to speed up. If it's going up the ramp, it's going to go up, and it's going to stop, and then it's coming back down again. So you'd have to specify delta x. So if you push it up the ramp, you could have delta x positive, which would be going this, here it starts here, and then you push it up. So you give an initial velocity up this way. What's going to happen is if you specify negative delta x, it's going to have to go all the way up and then go back down. If you specify the negative delta x, then there's only a finite distance it's going to go up before it stops. So you could have, if you've specified a negative delta x, it could be too large and you'd end up with negative time or something like that. Anyway, you can see that for this case of a ramp with no friction, it's pretty simple. A sub x is g sine theta. We did that in the lab. We figured that we measured the acceleration, and we found out it was equal to 9.8 times the sine of the angle of the ramp. So we've looked at something going on a flat surface with friction. Now we've got something on a inclined surface with no friction. The next thing will be having something on an inclined plane with friction. And then beyond that, you can have a mass hanging down under various circumstances. Those are some of the other later ones that you want to look at. Okay, let's look at another case. So if we have a inclined plane at some angle, and we put an object, a block or something, on this inclined plane, and let's have it initially in motion. So it's sliding down this, we'll call this V0. So it has some initial speed, and depending upon the angle, if the angle is low enough, it'll slow down and stop, and if the angle is large enough, it'll, if it's a particular angle, it'll actually just maintain a constant speed. And then if the angle is greater than that, then it will accelerate. So there's decelerate and stop, and this accelerate, or this constant velocity. Those are the three conditions. So stop, what we would have is that V, the final velocity, is known. If it accelerates, meaning it's a high enough angle, V is what we're going to have to calculate, and we'd specify the distance, delta x, along how far we want to measure, how far along here do we go, and then calculate the velocity. It's going to be greater than V0 because it'll be accelerating. So that's, if theta is small, this stops. If it accelerates, you have to calculate velocity, and you specify that. Now the actual calculation and the free body diagram are the same in either case. It's just how you use which one of these two the problem asks for. So just like the flat object, we have a force of friction that's pointing in the opposite direction that it's moving. We have the weight, which is pushing down like this, and we have the normal force. So let's draw those as just vectors. So we have the weight going down, we have the normal force going this way, we have the friction force going up like that. And because it's on a wedge, we're going to define x and y. Either, and that doesn't matter whether we define x going up or down. In this case, I decided to do it down. So this is the normal force, this is the friction force, this is the weight. And really the only difference between this and flat is that we break the weight up into a component that is perpendicular and a component that's parallel to the surface. And remember this, which angle is it? If you draw the thing like this, this is theta. That's the angle of the wedge. Because you see, if I rotated this thing this way, the angle gets smaller. This thing rotates that way, which would make this angle smaller. So this is W sub y, and this is W sub x. So we know that, and so we're going to mark that out and replace it with the component. So W sub x is equal to W times the cosine of the angle, or the sine of the angle, because it's the opposite side. So the sine of theta, and W sub y is equal to W times the cosine of theta. So if theta is 0, there's no x component, there's just the y component. And also remember that W is just mass times acceleration due to gravity. So we get mg sine theta here, and here we get mg cosine theta. So those are the components. So again, if we sum the forces in the y direction, In the y direction, it's not moving. It's sliding parallel to this surface. So W's force in the y direction equals 0 because the acceleration is 0. Now, not the forces are 0, but some of the forces is 0. So the way I define y positive, that's going to mean the normal force is positive and W sub y is negative. Therefore, the normal force is equal to W sub y, which I know here is equal to mg cosine of theta. And if I do it in the x direction, I do have movement there. So I have some acceleration. So I have the mass times acceleration in the x direction. And the way that I've defined x positive going up, that means the friction force is positive and the W sub x is negative. I know what W sub x is from there. The friction force, again, when you have friction force, you have to relate those by the fact the friction force is equal to the coefficient of friction times the normal force. But just like we did in the flat case, the normal force is equal, we've already calculated that through here. So we set these equal to each other from the sum of the forces in the y direction, and this was from just the geometry of the problem. So friction force is mu times normal force, which is mg cosine of theta. So now, just like before, I can substitute that in. Okay, so the left-hand side stays the same. The friction force is equal to mu mg cosine of theta. And the weight in the x direction is mg sine of theta. So depending upon what the relative magnitude of these two parts is, it's either going to be accelerating, which means if you had a positive acceleration, that means it's going to slow down, because positive means I'm accelerating in this direction, but I'm moving in that direction. So a sub x negative means slowing down. That's because the acceleration is in the opposite direction that it's initially moving. And a sub x positive means actually, is that the right way? I think it's the other way. Actually, sorry. So, yeah, I got it the wrong way around. So, a sub x negative means that the acceleration is in this direction, which means that it's speeding up. And acceleration positive means, so positive means the acceleration is in this direction. And because the velocity is down, that means slowing down. So if this component, the x component of the weight, is in size is greater than the friction force, then it's going to be speeding up. And that happens when this angle is large enough. If the angle is small, what will happen is this term will be bigger than that term. You'll have positive acceleration, which means it's going this way, positive, which means it's going to slow it down and ultimately stop it. Now notice again, I have mass in each part, so acceleration is then going to be mu g cosine theta minus g sine theta. And I just realized that this problem is where I do have friction. Okay, so this is, I'll have to go back and do the one you don't have friction. So but anyway, this is one you have friction. So you can still have it either speed or slow down. If you didn't have friction, it would always speed up because there would be nothing to slow this thing down. So that gives you the acceleration in the x direction. So if I'm given the initial velocity, which in this case would be negative because it's going down the inclined plane, and so that's v0, and v is equal to 0 meters per second. Then I know that I probably have been given a low enough angle that this thing ends up being negative. So here you'd have a sub x, which is negative. Otherwise, it doesn't make sense. So one case, the first case that we talked about was stopping. In that case, the acceleration has to be negative, and the initial velocity is also negative. Did I do that right? Oh, this is positive. Okay. So if a sub x is positive, then it's going to slow down. Okay, so that's pushing. Okay, then the other case would be where you're given v0, which again, if the way I define the coordinate system, it would be negative still going down. V would be the question mark, and a sub x is, in this case, positive because it's going, is negative because it's going in the opposite direction that I've defined. Positive x. It might have been better if I defined x positive going down. It probably would make more sense, but it still works out. So as long as you're consistent. In this case, you'd have this, and that, and you could calculate delta x and t. In this case, delta x would be negative because it's going down. And here, you would have to specify, since you're not specifying the final velocity being 0, you'd have to specify delta x, which would be negative because it's going down the ramp. And so you'd have delta x, which is negative, v0, which is negative. You'd have a sub x, which is negative, and then you could calculate v, again, using v squared is equal to v0 squared plus 2a delta x. And because it's, in the second case, it's speeding up, going down, so it's just v would also be negative, just a lot more negative than it starts out as. And then you have the other equation that says, v equals v0 plus at. You could solve to the t, knowing these are the three things. If I had to find x positive going down, how would that affect everything? If I just change my coordinate system, I'm just going to show you how that works. So I'm going to go through the same calculation, except I'm going to say x is positive going down instead of going up. So this one stays the same because that's the sum of the forces in the y direction. In this equation, because down is positive, this would become negative, and that would become positive. So this would be negative, and that would be positive. And therefore, these would be opposite. So a sub x negative would mean that you're pushing this way, you're accelerating this way, so this would be slowing down. And a sub x positive would, in this case, be speeding up. When you get over here, this would be negative, that would be positive. So when you have this problem, sliding down would be positive initial velocity. If it's slowing down, the acceleration would be negative, and you would calculate delta x and delta t. In this case, delta x is positive. To the second part, where you're given the initial velocity, again, the initial velocity would be positive because it's going down the same direction as positive x. For the thing to speed up, you'd have to have the acceleration in the same direction as the defined axis, so that would become positive. If you specified the distance down the ramp, now that would be positive quantity. The calculated velocity would be positive. So that's the difference, how it would work. So whichever way makes more sense to you, you can do it that way. So we're going to progress through different levels of complexity, and as far as these Newton's second law problems, so I think that's the best way to proceed instead of just giving you a complex problem to start with. So this is basically a table, and we're going to have some kind of thing on here, a block, and then we're going to have a pulley. Excuse me. And there's going to be a connection between this is a rope of some kind. This is over a pulley. And for Chapter 4, we assume that the pulley has no mass and no friction. And what that does for us is it means that we just use the pulley as a way to transfer the force from this mass that's hanging to this mass that's stationary. So the first simple case is no friction. So we have an object with mass m1, we have an object with mass 2, we have a cable connecting the two. There's no friction between these two, so the normal force, the y direction of this element really doesn't come into play. And let's just get some numbers here. Let's say the mass m1 is 2 kilograms and mass 2 is 5 kilograms. So as you can imagine, what's going to happen is this thing's going to, the force due to gravity is going to pull this down, and it's going to drag this thing along. But it's drag's maybe not the right word because there's no friction. It's going to move this thing. So what we do is we define a coordinate system, but we're actually going to define two coordinate systems. So I'm going to call this x1, y1, and this x2, y2. But it turns out that the y direction here doesn't come into play and the x direction doesn't come into play. So if we look, what we do is we draw free body diagrams for each element. We don't have to do it for the pulley because that doesn't have any mass or friction, so it's not really, there are forces involved, but it doesn't factor into the whole thing. So if I draw the free body diagram on this, I do have a weight pulling down, and I have a normal force pushing up, and they're exactly equal to each other. So weight has to be matched by that because the sum of the forces in the y direction equals 0 because it's a solid surface. And that just says the weight negative the weight is equal to positive the normal force. That's all it tells us. We don't need this because there's no coefficient of friction involved. The one that's important is that the sum of the forces in the x direction on this. So what's happening in the x direction? Well, you have a tension on this cable. This tension is going to pull this thing to the right. And I'm defining x positive in this direction. And then because it is moving, it's equal to, the sum of the forces equals the mass times the acceleration in the x direction for object 1. And so we look at the forces, and the only force acting on it is this tension, T, capital T. If there was friction, there would be another force, but we'll worry about that in the next problem. So we have T, it's pointing in the positive x direction. So that is all that's associated with this. As long as there's some tension on this cable, it's going to move to the right, and the tension is provided by this other block. Then we have the second free body diagram. And this tension that's coming is coming from this block at the bottom. So this is the T. So this tension is pulling it to the left, and this tension is holding this back. If there's no tension, it would just fall. If there's no rope, cut the rope, it's just going to fall with the acceleration due to gravity. But because there's this tension provided by this other mass that needs to be accelerated, it doesn't accelerate quite as quickly. Then you have the thing that's driving this whole situation is the weight. So there's the weight. I'm going to make it longer than T. And the weight is equal to, which call it W2, is M2 times G. The weight of an object is its mass times the acceleration due to gravity. Let's define positive y going up, positive x going here. Well, there's nothing happening. No forces at all in the x direction, so we don't even need to write it down. And let's put a subscript 1 up there for the first one. So now what we're going to do is we're going to sum the forces in the y direction for object 2. That's going to be equal to the mass times acceleration in the y direction for object 2. And the two forces that are acting on this body are going to be the tension, which is pulling in the positive direction, and the weight for object 2, which is pulling in the negative direction. So I have two equations. This one and this one. So let's just write those down separately over here. So the mass of object 1, make sure I put the right masses, I put the subscripts in here. Okay, so the mass of object 1 times the acceleration in the x direction of object 1 is equal to the tension. The second equation says the mass of object 2 times the acceleration in the y direction for object 2 is equal to the tension minus the weight. So what do I know? We know M1. We know these are the knowns. M1 and N2. We don't know tension, so our unknowns are A sub x1, A sub y2, the tension, and the weight of object 2. So we have basically 4 unknowns in these two equations and 2 equations. So we're going to have to figure out 2 more equations. So what are they? Well, the weight, so let's call this equation 1, we'll call this equation 2. We need a third equation, third and fourth equation. So W2 is just equal to the mass of object 2 times the acceleration due to gravity. So that gives me one additional equation. G is 9.8, positive 9.8 meters per second squared. The fourth one is that because these two objects are connected, that the acceleration of this has to be the same as the acceleration of that, even though they're different directions. They're connected by a rope, and so their relative positions, their relative accelerations are the same. Their accelerations are the same. One thing you have to be careful about is the sign. This one, when this moves from left to right, which is positive x, this one goes down, which is negative y. So what we can say is that A sub x1 is equal to negative A sub y2. So we always have to look at the direction that the objects will move. If one moves one direction, the other one's going to move a predictable direction. So now we have 4 equations and 4 unknowns. So again, you don't have to solve simultaneous equations. We're going to use substitution. So this one we can substitute in there, and it doesn't matter. Let's just substitute that in, well, we already solved for that, so let's plug that in there. So the first equation with this substitution becomes m1 times negative a sub y2 is equal to t. The second equation, m2 times a sub y2 is equal to the tension minus W2, but that's m2 times g. So now I have two unknowns, the acceleration and the tension. So I've already solved for t here, so I can then substitute that into there. So I'll get m2 a sub y2, this term, is equal to negative m1 times a sub y2 from this substitution. So t is equal to that, but it's also equal to that, so I can make that substitution. And then I have the second term like that. So the only unknown I have now is the acceleration of the object falling down. So I'll move this term to the left-hand side to get all the terms that involve a sub y2 to the right-hand side, the left-hand side. I'll factor out what I'm trying to solve for. And then I divide by the term in the parentheses. And that's the final answer. So what does that mean? It means that a sub y is going to be negative, which I knew, because if I let go of this thing, it's going to go down, which is opposite direction of positive y. So that's good. This is the driving force. This is the weight. And then these two are basically the total inertia of the system. Remember, mass is a measure of the inertia of a system. And so I've got two parts to accelerate. I've got the block hanging down and the block on the side. But I only have one of the blocks which is actually causing the thing to, the force that's moving this thing. So this is kind of like the force divided by the mass is equal to acceleration. So that all makes nice sense. In our case, I gave 2 kilograms and 5 kilograms. So I can calculate the acceleration for our particular example. It's going to be negative m2, and 2 was 5 kilograms times g, which is 9.8, positive 9.8 meters per second squared, divided by the sum of the two masses, my total inertia. And you know, the bigger that m2 is relative to m1, the faster it's going to accelerate. If m1 equals 0, then I just get negative 9.8 meters per second squared, because these cancel out. This goes to 0, so those cancel out. And I just end up with negative 9.8 meters per second squared. So I'll get negative 5 times 9.8 divided by 2 plus 5. And I get negative 7.0 meters per second squared. So that's the acceleration of object 1. Now I could go back and calculate the tension if I asked, what's the tension in the rope? And so the tension is just equal to negative m1 times a sub y2. I'm just using this equation, just simplifying it by taking away the parentheses, moving the negative side out front. So the tension is negative m1, which is 2 kilograms, times the acceleration, negative 7.0 meters per second squared. That gives me 14 kilogram meter per second squared is a newton. The negatives cancel out. So the tension, as I showed it, is the correct tension. This is positive. But if I guessed the wrong direction, then I would get a negative number, and then they say, oh, I did it wrong. Okay, so those are the two possible things. The accelerations are going to be the same, except a sub x1 is going to be positive. 7 meters per second squared. So let's just write that down. So a sub x1 is equal to negative a sub y2. So I have negative a negative 7 meters per second squared, which makes it 7 meters per second squared. So that is a sub x1. So the next complicating factor is if we add friction to the whole thing. So we'll do a separate video on that. And actually what we'll do is we'll just use this as a basis and just show you how things are different instead of redoing the whole thing. So the last problem we looked at was we had this situation. But now we're going to put friction in here. So let's see how things change as we put friction. So one thing that changes is this top block. So now we have a friction force that's pushing opposite direction of the motion. So this equation, instead of just being the tension, we're going to have minus F sub F, the friction force. So we're introducing one more unknown, so we're going to need one more equation at some point. The second object, nothing changes because it's still hanging down. So let me put another box around this one now that I can make a bigger box. Okay, so we add the friction force, but we add one extra unknown. Before we didn't have this, so we came and wrote these equations. So this equation now has negative the friction force, and therefore we have one more unknown. So the equation that we have is the one that relates so we have the kinetic coefficient of friction is the ratio of the friction force to the normal force. So that's the friction is the coefficient of friction. So we have to specify that. So let's go back to the beginning and let's specify the coefficient of friction. And I'm going to say it's the kinetic coefficient of friction is 0.30. So we've added one equation, but we still have actually one unknown. And I think back here, we didn't use this last time. But, so really we have a sixth equation that we didn't use last time, which was this one. And that would say that the normal force is equal to the weight. So that's also, the normal force is also another unknown. So I added two unknowns, so I have to have two more equations. So now I have 6 equations and 6 unknowns. Again, that seems daunting to some extent, but all we're going to do is we're going to do some more substitution. We're going to substitute this into there so that the kinetic coefficient of friction is equal to the friction force divided by the weight of the object. And this is actually W1. So actually we have another unknown, but we also know, so equation 7 is that W1 is equal to M1 times G, just like W2 is M2 times G. Okay. So actually I could substitute that into here and then substitute it there. So this becomes friction force divided by M1 times G. And then if I solve for the friction force from here, I can substitute that into here. So let me do that. Let me use green. So solving this one for the friction force, it's equal to the kinetic coefficient of friction times M1 times G. Okay, now I'm going to substitute that up here. So, so this original equation 1 has minus F sub F but f sub f is mu sub k times m times g. Okay, the second equation didn't change any, and this is m1 times g. So if we, in this case, we didn't have to solve for t because we already solved for t. So let me add a page and just do this extra step. So I have two equations and two unknowns. The two unknowns are the tension and deceleration. What I did previously is I just said, okay, t is equal to this, and then I plug that in there. So what I've got over here is I'm going to have to solve for t. So I'm going to have negative, this term, negative m1a sub y2, and then I'm going to have plus u sub k m1 times g. So that's what the tension is, based on the sum of the forces in the x direction. I guess that should be, yeah, x direction. That's where that came from. This substitution here I still did, and it still applies. So originally what I had was this. For a sub x, I put in negative a sub 2, which still applies in each case, the same for both examples. And then I added my friction force into the mix. So that's there. Changed sign when I moved it to this side so I could solve for t. So now I'm going to make this substitution, this t substitution, into this equation. So I'll have m2 a sub y2 is equal to the tension, but the tension is negative m1 a sub x, m sub a sub y2 plus mu sub k m1 g. That's just this substitution. This part is equal to t. And then I have the third term, which is minus m2g. So this equation only has one unknown, which is the acceleration, which I'm trying to solve for. So I'm going to do the same thing that I did before. I'm going to move this to the left-hand side. So I'll get m2 a sub y2, which is this term, adding m1 a sub y2 is equal to u sub k m1 g minus m2 g. If I factor out the thing I'm trying to solve for, what I have left is the sum of the masses. The right-hand side just stays the same. Okay, so this is a block sliding down an inclined plane. So if the angle is large enough, well, actually it doesn't matter. There's no friction. It's going to slide down, irrespective. So we take our little block, we bring it down here, and we show the forces acting on it. So we have the weight, and we have the normal force. So that's all we have in this case. That's the normal force, that's the weight. So if we clone those and bring them over here and center them as such. Oops, didn't mean to do that. Trying to get this thing. Let's try it. Not sure why I can't. Trying to get it so it puts a little cross there, but it doesn't. So anyway, plan B. Oh, there it goes. So we define the coordinate system. I'm going to define x going down because that's the way it's going to slide. Y is going up. So what we do is we convert the weight into a component perpendicular and a component parallel to the surface. The angle of the wedge is this angle here. So we'll have W sub y, and we'll have W sub x, and we'll have the normal force. So if we sum the forces in the y direction, going in the positive y direction is the normal force. Going in the negative y direction is the y component of the weight. And so this would tell me that the normal force is equal to the y component of the weight. But since there's no friction, we don't really need this. The only time we need the y equation is if we need to relate the normal force to the friction force through the coefficient of friction. So that's interesting, but it's not useful in solving this problem. If you sum the forces in the x direction, that's equal to the mass times the acceleration in the x direction. And the only force I have in the x direction is W sub x. The way that I've defined x positive going down, I'm going to say W sub x is positive. Now from geometry, we can see that the x component of the weight is equal to the weight times the opposite side from the angle, which is the sine. So it's the sine that we use. And we also know that the weight is equal to the mass times the acceleration due to gravity. So you see that the x component is mass times acceleration due to gravity times sine of theta. So I can plug that in, and so the weight is mg sine theta. Masses cancel out. So the acceleration in the x direction is equal to the acceleration due to gravity times the sine of theta. So if we had a problem like this, we could either start at zero velocity and calculate the final velocity. So one possibility would be, given that the initial velocity is equal to 0. They would say it starts at rest or something like that. We also know a sub x is equal to g times the sine of theta. So we have the acceleration, and we would figure out the velocity at some other time or distance. So you could specify either, you need to specify either delta x or t. Most of the time you'd expect to specify t. Delta x is positive because you would be sliding down the ramp, which is in the direction of positive x. So we'd have a positive value for delta x. T, of course, always is positive. So you can use, again, you can use v is equal to v0 plus at, or you can use v squared is equal to v0 squared plus 2a delta x. In the case of when it starts from rest, that's 0. Acceleration is going to be positive. Delta x is going to be positive, so you get a positive number here. So, the final velocity is the square root of 2a delta x, and then you could use that velocity to calculate the time. So even if they ask for, if you specify time, then you could use this equation to calculate v, and then you could use this equation to calculate delta x. It's either one. The second case would be that you're given some initial velocity. So you're given v0 equals some number. So you're given that. It's going to be positive. Well, if it's going down, it's positive. So you could have the initial velocity going up. So v0 up ramp would be negative some value. And v0 down the ramp would be equal to some positive quantity. Again, this up the ramp is opposite the direction that I defined positive x. So you'd have v0 negative, and then if you push it down the ramp, get it started going down the ramp, it's going to be negative. Down positive. Okay, so you would be given some initial velocity we know that a sub x is g sine theta. So that's positive. So it's going to either, if it's going down the ramp initially, it's just going to speed up. If it's going up the ramp, it's going to go up, and it's going to stop, and then it's coming back down again. So you'd have to specify delta x. So if you push it up the ramp, you could have delta x positive, which would be going this, here it starts here, and then you push it up. So you give an initial velocity up this way. What's going to happen is if you specify negative delta x, it's going to have to go all the way up and then go back down. If you specify the negative delta x, then there's only a finite distance it's going to go up before it stops. So you could have, if you specified a negative delta x, it could be too large and you'd end up with negative time or something like that. Anyway, you can see that for this case of a ramp with no friction, it's pretty simple. A sub x is g sine theta. We did that in the lab. We figured that we measured the acceleration, and we found out it was equal to 9.8 times the sine of the angle of the ramp. So we've looked at something going on a flat surface with friction. Now we've got something on a inclined surface with no friction. The next thing will be having something on an inclined plane with friction. And then beyond that, you can have a mass hanging down under various circumstances. Those are some of the other later ones that you want to look at. So now I'm going to take the friction off. So now we are going to have friction. Let's say the coefficient of friction equals 0.30 again. This is our kinetic coefficient of friction. Now there is a case where if this friction was high enough and the angle was low enough that things would not move. We're not going to consider that scenario. We're assuming that this mass is big enough that it's going to, and this angle is big enough that it won't, the friction is small enough it's not going to cause this thing to stop. So this is the previous free body diagram we had. The only difference is that now we're going to have this friction force acting here, which is going to oppose the motion. So I have one more unknown, and that goes right here, and it's going to go in the negative x direction. This one stays the same. The normal force is still the same. But we are going to use this because I have this one extra equation. I end up with one extra, I have one extra unknown, so I'm going to need one more equation. And this is the vertical element, which doesn't change because there's no friction involved in that at all. So I'm going to write the two equations. I'm not going to just copy what I did before. So we have m1 times w sub x, no, sorry, a sub x1 is equal to the tension minus w sub x1 minus the friction force. So I got that one extra term on there. And the second equation is from the second object. So this is the difference of the friction force. So the knowns are masses, the angle theta, and the coefficient of friction. The unknowns, which are not specified but can be calculated, are a sub x1, a sub y2, t, w sub x1, friction force, and W is 2. So now I have 6 unknowns and only 2 equations. But all the other equations are the same, pretty much. What we knew is, so let's go here. W2. So let me number these. 1, 2, 3. W2 is equal to M2 times G. So there's one more equation. W sub x is equal to W times the sine of theta. But that introduced another unknown, so I'll write that down. So now we need 7 equations. So W, this is W1. W1 is equal to M1 times G. Now we have the friction equation, which says that the coefficient of friction is the ratio of these two. Oh, got another unknown here. So the let's do the acceleration one. So a sub x1 is equal to negative a sub y2. So my last equation is from the sum of the forces in the y direction, which said that the normal force is equal to W sub y1. Okay, I got another unknown, W sub y1. But W sub y1, or 1y, I guess y1. Not sure which way I did it. W sub y1 is equal to W1 times the cosine of theta. I know theta, I know W1. So now I have everything I need. Got 1, 2, 3, 4, 5, 6, 7, 8, 9 unknowns, 9 equations. Again, it's not as daunting as it seems. You just have to make some substitutions. So this is W sub y. So I can plug that in there. So I know that the normal force is W sub y1, but that's W1 times cosine of theta. But W1 is equal to M1G then times the cosine of theta, which I can plug in to here. Actually, what I'm going to do is solve for the friction force. It's equal to mu times the normal force. But the normal force is equal to M1G cosine of theta. Okay, I'm going to plug that one in there. W1 goes there, so I can say W sub x1 is W1, but that's M1G sine of theta. So let's draw some arrows now. So that's going to go here. This is going to go. It's going to go there. T I don't solve for, and W2 goes there. So I think once I make all the substitutions, I'm going to have 2 equations, and I'm going to do it right down here so I can see it all. So I'm going to have M1 A sub x1 is equal to T minus W sub x1, but that is M1 G sine of theta. So that's that part, minus the friction force, which is equal to mu M1 G cosine of theta. So that's the first equation, and then that's equation 1 rewritten. And then I'm going to have, okay, I need to also do this acceleration substitution, which I didn't do yet. So I'm going to have M1 times A sub x1, which is equal to negative A sub y2. Okay, now, second equation. M2 A sub y2 is equal to T minus W2, but W2, the weight is M2 times G. So those are the 2 equations, and I've got 2 unknowns, acceleration and tension. So I'm going to do the same thing. I'm going to solve the second equation for tension. That'll be M1 A sub y2 plus m2 times g. And then I plug that into here. First equation. So the first equation becomes, so this is the second equation rewritten. First equation becomes minus m1a sub y2 is equal to the tension, but the tension is m1a sub y2 plus m, is that right, or is it, yeah, a sub y2, plus m2g, and then I have these terms there, m1g sine theta minus mu times m1g cosine theta. Now, I'm trying to solve for a sub y2, so I'm going to move this to the other side. So I'll get negative m1a sub y2 minus m1, oh, something wrong here. I think I messed up with the, oh, this should be m2. So that's m2. So that's m2. So this is m2. A sub y2 is equal to m2g minus m1g sine theta minus mu m1g cosine theta. So I factor out the unknown. Again, I'm going to do what I did last time. I'm going to change the sign of these, everything. I'm going to change the sign of everything. So these will become positive and that will become negative. So I'll have m1g sine of theta plus mu m1g cosine of theta minus m2g. And then I divide by the term in the parentheses. So the numerator will be just the right-hand side. The denominator will be the sum of the masses. So again, the denominator is the total inertia of the system. And the numerator, you've got, this is wanting to make the thing drop. These two things are slowing it down. One is the mass of the object and its corresponding weight in the x direction. And this is the friction, which is also opposite, acting to slow it down. So if we, what do? If we let theta equals 0, what happens? Well, the sine of theta equals 0 and the cosine of theta equals 1. So under those conditions, we get, this term goes to 0, we get mu m1g minus m2g over m1 plus m2. This is a case that we looked at with the flat table, and you'll find out that it's exactly the same equation we ended up with in that simpler case. If theta equals 90, the sine of theta equals 1 and the cosine of theta equals 0. So this term goes to 0, and we just end up with a sub y is equal to m1g minus m2g divided by m1 plus m2. And so this is that Atwood's machine with the two masses hanging over a pulley. And the friction doesn't come into play because the normal force is 0. So even though there might be something there, it's never touching. The touching force is 0. So it ends up reverting back. So the case with friction or no friction, the Atwood's machine, unless you push one of those masses against something to create some friction, it's not going to have any friction. So you can see we're getting more general as we go along. What more stuff could I do here to make it even more general? Well, I could have this mass, instead of hanging, I could have it on another plane that's at an angle. So that, and then you can have that without friction or with friction. We don't need to get that complicated. But the basic idea applies for all situations. You do the free body diagrams for both the masses. The connection is the tension and the acceleration. When we do Newton's second law, we end up with two equations, but usually a lot of unknowns. So then we have to see what we don't know and then use things such as the weight is equal to the mass times g, that the x and y components on a plane are the weight times the sine of theta and weight times cosine of theta. We use the fact that the accelerations are the same magnitude, but possibly the same or different signs depending on how we define the coordinate system. We relate the normal force to the friction force through the coefficient of friction, and so that's how it works. So let's look at let's look at the case. Let's just plug some numbers in here. I don't think we actually ran a theta. So let's theta equal 25 degrees. Mu is equal to 0.30. M1 equals 2 kilograms. M2 is equal to 5 kilograms. So the acceleration, again, should be less than 9.8 or more, between negative 9.8 and 0. Okay, so we have M1, which is 2 kilograms, times G, which is 9.8 meters per second squared, times the sine of 25 degrees, plus coefficient of friction, times M1 times G. I'm going to leave the units off because I'm running out of space here at the cosine of 25 degrees, minus M2, which is 5 kilograms, times G, which is 9.8 meters per second squared. So that's the numerator, and I divide that by the sum of the two masses again. So this should be even smaller than we had before because it's all things that going to slow things down. So 2 times 9.8 times the sine of 25 degrees plus 0.3 times 2 times 9.8 times the cosine 25 degrees minus 5 times 9.8. It's negative 35.4 divided by 7, the sum of the masses, and I get the acceleration is negative 5.1 meters per second squared. So I think we had 7. We had a friction, we went down to 6, and then we had the inclined plane, which decreases it even more because we also have to overcome gravity on the mass M1.